Let's talk about something you probably see every single day, but maybe don't give a second thought to: the gear. It seems so simple, right? But it turns out there is an incredible world of science and really brilliant engineering hiding just beneath the surface.
I mean, have you ever really looked at one up close? That gentle curve on each tooth? That's not just a random shape or something for aesthetics. Oh no, it's a precisely engineered curve that honestly makes our entire modern world possible. And today we're going to find out exactly why.
So here's the plan. We'll start with the gear shape you see everywhere, then check out some really specialized, kind of weird ones. After that, we'll see how engineers fine-tune individual teeth, dive into some seriously high-performance stuff, and wrap it all up with the wild digital modeling that makes it all happen.
All right, first up, let's get into the absolute workhorse of the industry, the shape that you'll find on the vast majority of gears out there. It's called the involute curve.
So what in the world is an involute profile? Well, the best way to get it is to picture this. You've got a spool of thread. Now imagine pulling that thread so it unwinds but you keep it perfectly tight. The path that the very end of that string makes as it comes off the spool, that is an involute curve. It's that simple, that elegant, and it's the absolute foundation of modern gear design.
So why is this one shape the undisputed king? Well, it's got some killer advantages. First off, it gives you a perfectly constant velocity ratio, which means super smooth power transmission. No jerking, no stuttering. It's also surprisingly forgiving if the gears aren't lined up perfectly, and it's relatively easy to manufacture. And this isn't just theory. Researchers like Zhang and their team pointed out in 2023 just how crucial this specific geometry is for keeping contact stresses low and efficiency high.
But, one size doesn't fit all. The involute is amazing, but it's not the only game in town. For really specialized jobs, engineers had to get creative and come up with some very unique shapes.
So think of it this way. Your standard involute gears are the go-to when you need steady, constant speed. They're the reliable daily driver. But when a machine needs something special, like a speed that changes during rotation or really unique contact physics, that's when engineers reach for a whole different toolkit, the non-involute gears. Let's look at a couple. Cycloidal gears, for instance, have this really unique surface curvature. And what that does, according to research from Zavialov, is it leads to lower contact stress. That's why they're absolutely perfect for tiny, delicate machines like watches and clocks. Then you've got something like elliptical gears. These are wild. They're designed on purpose to create a non-uniform speed, which is exactly what you want for certain kinds of automated machinery or industrial mixers that need a variable push. Okay, so we've covered the big picture, the overall profile of the gear, but now we're going to zoom way in, right down to the tooth itself, because this is where the real artistry comes in, modifying a single tooth for absolute peak performance.
You see, even a perfectly calculated involute tooth can have an issue. As two gears are meshing, the very tip of one tooth can bump into the other one a little too early. That causes a nasty spike in stress and makes things noisy. The solution? It's called tip relief. It's where engineers shave off just a tiny, microscopic amount of material from the tooth's tip. And as Pedrero and his team found in 2023, this one small change makes a huge difference. You get a much smoother mesh, way less stress, and the gear lasts a whole lot longer.
Now, most of what we've talked about so far kind of assumes that the gear is going to be working in both directions, right? Clockwise and counterclockwise. But what if it's not? What if the force is always a one-way street? Well, that's when you call in the specialist, the asymmetric spur gear. In things like power generators or heavy-duty winches, the torque is pretty much always going in the same direction. So engineers brilliantly redesign the tooth so that its flanks, its sides, are optimized for that one direction of force. And according to the work of Allman, DeSalvis, and Gonsalves from 2021, this clever trick can massively boost a gear's load-bearing capacity and its resistance to wear and tear.
Okay, so tweaking a single tooth is one thing, but how do you level up the entire gear system for maximum performance? Well, that brings us to the world of high-performance gearing. And the big idea here is simple: share the load.
2 plus. What on earth could that mean? It's not just some random number. This is a whole design philosophy, and it is a total game changer.
It stands for the number of teeth that are in contact at any single moment inside a high contact ratio gear, or HCR gear for short. See, in a standard gear, all that force is being slammed onto just one or maybe two teeth at a time.
But HCR gears are designed so that you always have at least two, sometimes more, teeth sharing that load. Spreading the stress out like that means less wear, less vibration, and a much, much quieter machine. And as folks like Tehran and Salman showed in 2024, engineers are now building incredible tools to push these designs way beyond what we thought was possible.
So, you're probably asking yourself, how do engineers actually design, test, and prove all these incredibly complex shapes? I mean, they can't just build 1,000 prototypes, right? This takes us to our final stop, the digital frontier of gear modeling.
This quote right here from Brazone's research in 2021 just nails it. The old school simplified math formulas, they just don't work anymore. To really know how a gear is going to behave under real-world pressure, designers now use these unbelievably powerful computer models that can simulate exactly how a tooth will bend, flex, and deform with mind-boggling accuracy.
This means they're using a whole suite of digital tools. You've got tooth contact analysis, or TCA, to check the basic geometry. Then you've got loaded TCA, which simulates what happens when you actually put force on those teeth. And then there's the heavy hitter, finite element analysis, or FEA, which is like giving the gear a full-body MRI to see every single stress point. These tools are so good, as Vignesh and Mertens demonstrated in 2024, that they can even design gears out of new materials like thermoplastics, predicting exactly how they'll behave. And that really brings us to the big final thought here. When you step back and look at this journey, from a simple curve traced by a string all the way to these insane digital simulations, it's all about perfecting one of the most fundamental building blocks of engineering. So that leaves us with a question. If we now have the tools and the knowledge to design the absolute perfect gear for almost any task imaginable, what are the limits? What can't we build?